Hey, and welcome to the isoPoint training series. I'm Eric with Aktina, and today I'll show you how to create and measure an iMarc dataset to find your LINAC physical isocenter. If your isoPoint hardware is already set up for the workflow, you're all set. If not, take a moment to check out the optical tracking hardware and software setup videos linked in the description below. Now, let's dive right in. First, expand the project tree and double-click on the session you want to work in. This will take you straight to the Session tab. Quick note, if you plan on measuring a couch axis dataset to determine how close it is to your physical isocenter, make sure to measure the couch axis dataset first. You can't measure the iMarc before the couch. To see how to create and measure a couch axis dataset, check out the video linked in the description below. So to create an iMarc dataset, click on the New iMarc button here. A dialog will pop up prompting you to input for which gantry angles you want to measure the collimator axes. At a minimum, the 4 cardinal gantry angles are required to accurately determine physical isocenter. To add more angles, simply include another comma-separated value. It's common to add both positive and negative 180 degrees, as this provides insight into the full gantry behavior and helps establish a robust baseline. By the way, the negate button simply inverts the signs of all the gantry angles that are currently listed in the field, effectively reversing the order of data collection. After creating an iMarc dataset, you'll now see the measurement items listed in the tree, and they will correspond to the gantry angle in the order you entered them when creating the dataset. In the new iMarc dataset, you'll also find the physical isocenter tree item and 2 reports, the physical isocenter report and the mechanical isocenter report. These reports will be computed once all measurements within the dataset are complete. The physical isocenter report is covered in depth at the end of the video. The physical isocenter tree item will display the radius of your physical isocenter once measurements are complete. Remember that physical isocenter is the smallest sphere that is intersected by all the measured collimator axes. For more information on the physics of isoPoint, feel free to visit our website linked in the description below that contains additional resources like physics papers that discuss the physical isocenter framework. Now for the action. Let's begin the measurements. Quick tip, there are 2 ways to start measuring: by clicking the acquisition button with a single measurement selected in the tree, or with a dataset selected in the tree. Starting with a dataset selected, we'll start a workflow for measuring the entire dataset. Starting with a single measurement, we'll start a more limited workflow intended for just that one measurement. Select the dataset in the tree and click the acquisition button to open the measurement control panel, initiating the workflow to measure all the collimator axes in the dataset. Set the gantry angle to match the value in the first measurement in the tree and unwind the collimator all the way in either direction. When you're ready, click the record button and then begin rotating the collimator through its entire 360-degree rotation. After completing the full rotation, click the Save Data button to save the rotational data and compute the collimator axis of rotation for that gantry angle. Set the gantry angle to the next measurement and then repeat the measurement process. First clicking the Record button, then rotating the collimator fully, then clicking the Save button. Continue until all measurements are complete. Once the iMarc dataset is fully measured, your physical isocenter will be automatically computed and its radius will be conveniently displayed in the session tree. Remember, physical isocenter will serve as our landmark for isocenter optimization. The couch axis of rotation and the radiation isocenter will be set to this important location. The physical isocenter data is displayed in the physical isocenter report in detail. The first section beneath the header, labeled Collimator Axis Errors, shows how close the collimator axes are from the physical isocenter, projected onto the 3 Cartesian planes. Each dot is color-coded by gantry angle. All 3 plots in the section have an origin set to the physical isocenter, and the red circle shows the physical isocenter radius. Pro tip: the spread between the gantry 0 and the gantry 180 axes in the first XY plot indicates your gantry sag and generally defines the radius of the physical isocenter. Beneath the graphs, you'll find a table showing the exact distances of the collimator axes from the physical isocenter, with the maximum value being the physical isocenter radius displayed in the table header. These plots provide valuable insights into potential mechanical issues with the LINAC. For example, a collimator assembly error can be detected when the 90 and negative 90 collimator axes are offset from the origin, the Z direction. Next is the beam's eye view axis errors section. The graph in this section shows the same data points from the previous section, but in this case, the graph is in the beam eye view. These dataset provide further insights into the relationship between the collimator axes. For example, collimator assembly position errors will appear as a right-left shift in all the points relative to the origin. Finally, the Collimator Walkout section contains graphs which display collimator concentricity plots. For each gantry angle, the tracking data is overlaid on a circular fit, while on the right, any deviation from the circular fit is shown with the maximum error highlighted. All the data in this report will come in very handy when characterizing a new LINAC install and can be used to periodically check the mechanical performance of your machine. If you have any questions about the Physical Isocenter workflow, feel free to contact our support team at isoPoint@aktina.com. Enjoy using isoPoint, thanks for watching, and we'll see you in the next video.